Welcome everyone. This is Daniel Paez and I'm going to be your lecturer for Engineering 4010 System Engineering for Engineering. This course will equip you with essential skills in system thinking, problem solving and stakeholder management, crucial for engineering management. All of you that have decided to do a course in engineering management need these components to be able to be in the workforce, wherever you are in the world, and think the key aspects that engineers do in their thinking. This is going to be the first lecture. We're going to do recordings of every lecture. And in the first lecture, I'm going to help you understand what is important in the course and what key things you need to keep in mind to do well in the course and the concepts that builds this subject. So the outline of the course will be described first. Then I'm going to talk about defining system thinking, which is fundamental for all engineers, common terms that are used in system engineering, and exploring design and thinking in system engineering. We're going to start thinking how we're going to implement this in the real world. In your lectures, I'm going to help you by doing exercises, individual and group, that will build in this thinking, give you more details about concepts, and be able to help you with your day-to-day work. Something important, what the material I give you is just the start. There's many interesting and other materials out there, from YouTube videos to podcasts. There's an area of many things. System engineering is more important than ever today. If you think about all those SpaceX rockets that go up and then they catch back when they come back, those use system engineers. So we're going to describe some of those key concepts that they use to be able to do that and how you can apply them in every single situation that you might face in the future as an engineer. So what do I want you to be able to learn from this subject? The first one is to understand what system engineering is. What is a system and what is complexity? Systems have different levels of complexities and that becomes very important to understand. Also, I want you to be able to have the ability to define system thinking. So you understand what is the difference between thinking through a problem, even thinking through a complex research problem, but adding the thinking like a system problem. And ideally, you also will learn key concepts. There's two concepts that we're going to talk about it that you can apply throughout the course. And as part of the description of the course, I'm going to be able to tell you what elements will be important for me to allow you to demonstrate that you have the knowledge of system engineering. So the course, here are my contact details, and the outline is in our learning system, so you can get all the details of the subjects with the key dates and the assignment descriptions and so on, and it becomes fundamental that you understand well what is expected of you in this subject. I will talk about more a little bit further. Here are my contact details, my email, daniel.p at uhe.edu.au. My phone number, you're welcome to ring me, particularly if there are problems with an assignment, particularly if you have a question or there's something important I can help you, you're welcome to use it. I use WhatsApp, SMS or calls, whatever suits you, and this subject or these notes are delivered for semester 1, 2025. So what is important? The course structure has been designed to help you develop system thinking and leadership skills. They go together. You will learn to analyze, design, and manage complex systems, preparing you for real-world challenges. Your first assessment is the professional portfolio, where would you reflect on your skills and set learning goals. We will start that process today. Assignment, the development of the assignment, we will start it with this video, and during the lectures, during the week, we will work on that so you understand what is expected in that assignment 1. Key topics: understanding complex systems, the system engineer life cycle and stakeholder management, and risk analysis and decision making. That's covered today. And very important, keep in mind assessment task. First one, professional portfolio, due week 3, group system engineering case study, week 6, and final system analysis goes between week 11 and at the end of week 12 or 13. That is the system engineering subject. 3 assignments that becomes very important that they connect one to the other. Your portfolio becomes very important to understand the other 2 parts of the assignment for the subject. Now, when I was a student, I always was curious to know why the top students do well. So the best thing to do here is that I tell you directly what are the behaviors I normally see in students that do well in subjects. So to pass, the first thing you need to know is that you need to prepare and attend the lectures. The second one is you need to read assignment requirements. A lot of the time people don't read their assignment requirements and they submit the wrong thing. Don't trust ChatGPT or an AI to do that for you. You need to guide the tool, you need to read it and be able to use it in such a way that you understand the assignment. So read the assignment and submit on time. If you submit late, marks will be deducted. It will be harder for you to do a good work, it will be harder to be able to be up there and deliver a good assignment. If you want good marks, read the extra material at the end of these lectures, the one that is in the outline of the subjects, the one that I give you at class. Read that material because that is the way that you get better at systems engineering. You read what is important. And participate in class. We're going to have individual activities, group activities. We're going to have the ability to write, the ability to speak, and so on. So participating in class will help you. Be active in class so you get an opportunity to challenge your ideas. And yes, it is part of engineers now to use AI, generative AI, like Gemini, ChatGPT, Cloud, whatever it is. But use it for what it is for, as a data miner, as improving your writing or whatever it is. Don't expect it to be able to learn from you. It's impossible. Now, top students do all the other things that I mentioned and are ahead of the teacher. They already know what we're going to see in week 2, so they are prepared in that and they start connecting concepts. They know sometimes more sources than me. And they ask questions, sometimes difficult questions, some questions that I don't know the answer, I have to go and research it. That is very good. And very important, they bring their passion into the class. They might be passionate about construction or mechanical engineering, electrical, whatever the area of engineering or design or architecture, urban planning, whatever it is, they bring it to the class. And they use that passion to generate interest and be able to digest the concepts. There's a lot of information out there. The key of a good engineer today is to be able to synthesize that information and be able to apply it in real situations. So constantly, I will try to drive you to be able to apply system engineering in every single situation of engineering that you might face in your professional career. Now, let's start by defining how we interpret the world. What is system engineering? Let's define that. And system engineering is an interdisciplinary approach to design and managing complex systems. So system engineering is a way that we engineers use to be able to deal with complexity. And it is applied in all engineering areas. I use it in urban planning and in civil engineering, when I'm developing software in the other subjects that I lecture. All those have to have a system component. I think as a system when I'm facing different problems. Sometimes they're very simple systems, like perhaps cooking dinner. Sometimes they're very complex systems, like taking a rocket to the space. All of those require the same thinking, which is the thinking that we're going to do it. So we use systems to simplify our world and be able to solve problems. Typical key benefits are managed complexity. So you actually have a way to manage it. You cannot reduce complexity in most cases. An urban system, a city, the public transport system, which I have worked a lot in Australia, is very complex. You cannot reduce the complexity, but you can manage that complexity to be able to solve individual problems, to get others to help you with problems, to do many things that really give you an advantage in that sense. Also, you reduce risk and cost. If you think like a system, you understand where are the main problems to solve and how can be improved. And enhance decision making. You taking technical or managerial decisions will take better decisions if you have system thinking. So that becomes very important, that the purpose of doing system engineering ultimately is to use resources more efficiently. Now, let's start with a simple example. Think of a self-driving car. It integrates mechanical components, software components, communication, data network, GPS, human interaction. System engineering ensures that all of those components work together effectively. This structured approach helps engineers prevent critical failures and optimize system performance. So what is system engineering? A system is a set of things interacting in a way that produces something greater than the sum of its parts. Typical example is a system is UHE, our school. It's a system. It has multiple parts to it. These systems work together to be able to develop an education system. So we understand that we put together things to develop bigger things. And that's when it becomes fundamental to have systems. And systems are all over the place. Sometimes we don't realize, but when we are interacting in the world, we already been part of a system, either because we interact with the system or because we require something for the systems, or we are part of the solutions of a system. So systems are that set of interactive parts that work together. Let's dig a little bit more in this concept. And the perfect example is because you're thinking, systems engineering is for designing. Yes, definitely you can use it for designing, but you also use it to find problems. And considering the Boeing 737 MAX crisis, it was a big event, big challenge to Boeing. I don't think Boeing, the big company, has been able to recover from a significant problem, which was the 737 MAX. 2 aircraft fell out of the sky. And it was a significant faulty of the autonomous system. And there were crashes, there were people that died, no? And when we look into that problem, there were poor stakeholder engagements, lack of risk analysis, inadequate verification and testing. There were multiple factors that didn't do it. So when we see big problems, 2 planes fall off the sky, then we also can think systems. So why systems allow us to both design the future and evaluate the present. If you tell me, how can we improve a particular part of the transport system, we will have to go into system engineers to try to find solutions. But at the same time, if you tell me, how can we design a better transport system, we will go into design. So system engineering allow the use in both presenting solutions to an existing problem or creating something new. They both are as valid, and thinking in system engineering allows you to do better in both areas. So let's start getting a little bit of conceptual design to system engineering, so you can start internalizing what is important to remember about a system engineering and what kind of things I need to keep in my mind every time I'm interacting in this subject and every time I'm trying to answer the assessment, particular assessments 2 and 3, which is where you're going to demonstrate you are acquiring the knowledge to be a good system engineer. So what are the characteristics of a system? All systems have a purpose. The transport system, transport people. The plane systems, fly planes. The taxation system charges taxes, and so on. There's always a purpose for a system. So you need to understand when you are looking into a design or a problem, what is the purpose the system. And every part that you're trying to put apart has a function. In a plane, you will understand every part will have a function. One that make it fly, the other one that communicates, the one that make it speed up, the other one to slow it down, and so on. So there are functions within the parts. If there is a part with no function, probably you have classified that part wrongly, or that part doesn't need to exist. And the performance of a system is affected by how the parts are arranged. If I put the engines in one way, it affects how the plane flies. If I invert the engines, the plane stops. If I accelerate the engines, they go faster. So the parts affects the function of the system. And as a general sense, you create systems so they maintain stability. Nature shows us that all the time. For example, hydrology. When you move water, water will try to maintain stability. The hydrographic cycle, when water goes to the sea and is evaporated into the clouds and comes back into water that rains and so on, is transported by the rivers and go back and so on, that cycle tries to keep stability. So most designs that we do and problem that we solve is to provide stability. Stability for a plane to fly, a train to transport people, a structure to be able to be operational and so on. Those systems want to be stable. And we normally design systems to have that stability in any way you want to describe stability. Then, what I want to generate in every one of you is the ability to have a system thinking, being able to enhance your perspective as an engineer and add a new key tool in your thinking process called system thinking, which means seeing the big picture. And it requires multiple parts, and I'm not going to go too much in detail in this video. We will see them in the lectures, and there's a lot of material around it. But key elements are interconnectivity, feedback loops, and emergent properties. What are things that could happen that we don't know? So system thinking involves expanding our awareness to see relationships between the parts that make up a larger entity. That's when a system engineer understands very well. He's able to put things apart. So, in practice, and we will do a group activity in the class, a system thinking you can apply to even what you had to eat today. Think about it. What was the process in the system of supply for you to be able to have the food that you have today? That becomes fundamental. And there was many components, someone producing, someone cooking, someone bringing gas to your stove so you could cook it, someone being able to power your fridge so the food was available, and so on. So there's many systems out there that actually, if you need to solve problems, you start unpack them and you see many interesting characteristics of them. And they all follow what I spoke before. They want stability. They want you to give you your food at a certain temperature so it's stable for you to eat. Now, they are very complex systems. A traffic system, for example, is very complex. A hospital system, it has medical staff, patient flows, equipment that need to use, and so on. So there are multiple parts of those movements. And we see problems, and that's what engineers are called, and there are multiple solutions, and thinking like a systems allows to say, okay, now I know that there's a purpose for that system, there are some components in that system and functions, and I want to keep the system stable. How I go into those things will depend on the problem, but I'm always going to look for those components, functions, and stability. Now, systems are very complex, and the automotive industry is particularly known for having the ability to produce very complex systems that are very stable. And this is an example on the screen. You can see a car, how many parts are put together and how many functions and systems are put together for the car to be able to run, to stop, to indicate, to communicate, to do many things, to open a door, to open the windows and so on. So parts are very important and allows you to understand that when you put them together, you have a car. This is called sometimes decomposing a system. You are able to put it apart and be able to understand it better. Now I can see what is underpinning the wheels, what is happening with the transmission, what is the suspension, and so on. The complexity of the system, I'm going to start wrapping up, one of the final parts of the lecture is about being able to understand the different levels of complexity. And as a general sense, we try to classify the systems in different levels. So the more levels you go, the more complex it is, the more people, the more engineers you need to do. And probably as an engineer, you will be working on one small function that has a significant design need or a problem to be solved in a larger team, and so on. Think about this. A screwdriver has 3 parts and is the simplest level of a system. But if you go to an airliner, a Boeing 737 has 100,000 parts, and therefore is the highest level of complexity. In the slides, you can see there is a formula to calculate the level of complexity you can have in a system. So, 2 more concepts for the first week. The first one is the system engineering lifecycle. Probably you have learned about lifecycle in every single subject of your course in engineering management. These apply again here. You know things need to stand from a concept, development, go to design, go to testing, and come back to operations. That is the part of a system. And every of that part of the cycle is defined differently. And in system engineering, we do the same. We have a cycle in where we learn how systems work through following that particular cycle. Now, 2 terms. We'll discuss it further. You need to read of them because they are fundamental for you to learn. The first one is feedback loop. In system engineering, yes, we care about the life cycle, but we do want to know what is happening in every part of that. Getting feedback loop. What is happening in my design? Getting feedback loop from stakeholders, from other designers, from other testings, for previous knowledge, and so on. And the other part, fundamental, is leverage point. We will talk more about in further classes, but leverage point is certain components has particular functions that have more impact than others. Like the system that heats up the food in a plane has less dependency and stability than the engines of the plane. So if you modify the engines, you have significant more impact than if you modify the oven that heats up the food in the plane. So understanding that becomes very, very important because you know that it could be a large part, could be many parts, but they have the leverage point is small, and that's part of doing system thinking. Finally, cultivating system thinking needs 5 components. I want to develop this throughout the 12 weeks of this subject. The first one, think critically. Second, ask questions. Third, look for connections. 4, consider multiple perspectives. And 5, remain flexible in your thinking. That is a good engineer. The one that has those 5 components. Don't worry, we will work on them throughout the 12 weeks. You got the descriptions in your material, but you know there are certain characteristics of all good system engineers, and you need to be aware of what they are and how you can start practicing in every system engineering problem. So, as a conclusion of this first week slides, I hope you have learned the importance of system engineering in managing complex problems. We reduce risk and we optimize resources. And that is important in that process. What are the different parts that are moving and what is important for the different parts that are happening. Now, it is important also to start working on your professional portfolio. In the lecture and the tutorial, we will work on that so you have clarity on what you need to do. And finally, the next steps are to read, because remember, I'm not giving you all the material. You need to read more when it needs to be done. More resources, they are in the outline of the class. Do not hesitate to contact me. And remember, the more you engage with the material, the better you will become a system engineer. See you in the next class.